Here I'm looking at a typical homework problem involving a rational function. That is a function with the polynomial on the numerator and denominator of this large fraction we've got here. And these can be tricky because they've got a lot of different features that we find using very different methods. What I'm going to do in this video is approach this problem using some technology like ChatGPT and Desmos to gain a deeper understanding of what's going on here. Now the first thing I'm going to do is right click on that, and I can actually copy this to the clipboard using a couple of different methods. I found that the ASCII is a little bit smaller and shorter. That's essentially what we would use to type into Desmos if we wanted to evaluate that. And the next thing I'm going to do is paste this right into ChatGPT. And if I just paste it alone, it might have some ideas of what it wants to do, like how to factor it, how to come up with some features, and it will really show a lot of steps in how to do that process, which that can be really helpful for us. Really can be kind of your own personal tutor to get you through some of these problems. There it used factoring by grouping to tackle that numerator and denominator. And it's going to give us that factored result. So that's really actually what I wanted to get out of this, just to get through that factoring part to something that's a little bit more useful for me. And then it's going to even go in and find a lot of these key features. So I'll let it go ahead and continue in that process. And all I want to do for this video is just copy that factored rational function. And I'll take that over to Desmos and paste it in there. And I can come back to this window later once I've examined what I see here. And as always, one thing that I like to do to help sort of center this is to edit that list and add a table of points, which can then be focused in and out. And I'm going to maybe want to change those points for this particular graph. I see that I've got a vertical asymptote. It's turning away, it looks like at x equals 1. And if I look back at my ChatGPT, I can definitely confirm that. So I'll go ahead and put that reference line. I like to make my asymptotes dashed black lines like that. And now I can see that it would be really nice to put 1 in the center. So maybe going from -2 all the way up to 1, and then even down to 3 to start to get more perspective. And sometimes what I'll do is add some spaces here and really start a ways back. So let me delete out all of these. This will be a little easier. Let's say I want to start at -5. Then I can go enter, go to -4. And now I just need to keep hitting enter on my keyboard, remembering that we have 1 in the center. So I probably want to go all the way up to something like 6 to really get a good view. And that actually helps bring things in a little bit and give us a little bit better view of that. That's what I like to use the table for. Of course, that takes up a lot of space. So if you want, you can add a folder and just put your table of points in that and collapse that out of the way. We also can turn off the plotting of those points, and that will then just be sort of a reference for us to use as needed. Another thing I like to do is just organize my features. I'll call this key features for another folder. And there we will have our asymptote first. If you want to add labels to really document this process, you can add in notes, and those can really be used effectively to label your work as you go. This is a vertical asymptote. And vertical asymptotes will always be x equals. I always kind of picture it as if I was drawing this on paper, I would put those little tick marks on the x-axis, and that would represent x equals 1, 2, 3, and 4. And if you extend those tick marks into a line, you've got a vertical line. So that's how we're going to view those vertical asymptotes. And we noticed back in the ChatGPT, it was talking about canceling a common factor. That's this 2x plus 3 here. We'll notice that at a value of -3/2, just solving one of these for x and bringing this back, you can see actually right here, that is exactly what they did in that step. They solved for x and got -3/2, and that will be undefined in this function. If you wanted to, you could add in that point. Let's see, where would that be appropriate? At -1.5. So here's -3/2. That'll be an undefined value when we plug it into that function, f of x. So what we want to do is recognize that that factor will actually cancel and create a whole. I like to define a new function, g of x, with exactly that same input, just canceling the common factors, deleting out that 2x plus 3 from the numerator and denominator. And we see here, those are green and blue. I can make this green one dotted to really bring out the difference. That's exactly the same line. However, now, if I want to plot g of negative 3 halves, I can do that without that discontinuity, that 0 in the denominator. It really is a 0 over 0 that fortunately cancels out, so we don't have to deal with that problem. And there we can see at negative 3 halves, we would be at a value of negative 1 if we were able to plot that point. And one thing that I think can be interesting in Desmos is to really find the discontinuity, find the whole, as it's called, in this case in the blue line. The way I could do that is set my x value to negative 3 halves. Now this one, it's plotting a line that really, when we look at the graph, it's not steering away from that like an asymptote. It travels right through it. But what it will allow us to do now is to actually kind of click right at that intersection. Sometimes you'll even zoom in to get there a little bit easier. And we can see that there is a hole there. It just doesn't plot it because the points are plotted really getting very, very close to it. And so there's a missing piece there, but it hasn't really shown it to us with the way that it's graphing in Desmos. So I'm going to remove that vertical line and use this information to create a plotted point that will really show us that hole in the graph. Now I can delete out this g of negative 3 halves, or I can just make a modification and turn that into my point. So the x and y coordinates are for x, negative 3 halves, and for y, the g of negative 3 halves, or the value of the simplified function when we plug in that x value. So this works really great. We've got our x, g of x to find that point. This one is called the whole. It is a key feature, so I will drag it down in there and make it match. Really, I have a blue graph that I'm using there for my f of x function. Let's make that match with a blue dot. So I'm just editing my list, changing it to blue, and there's the option to create the whole. And now I'll add a note to label that. So I've got all of my key features labeled and I can tuck those away. The table of points is there. We can bring this back to focus. Let's put those points back on and zoom it to fit. Now I don't need those and I can put that away. So a lot of functionality to these folders aside from just making it look nicer. Now there's the whole at negative 3 halves or negative 1.5. I can even do a little more and add a label to that. If you watch some of my other videos, I talk about making actually dynamic labels. So a label that might say whole, colon, and then the value with it. So check out some of my other videos on plotting points and creating labels if you want to get into that. Now there's maybe a couple other features that I could point out here. For example, the end behavior. In this case, we see this behavior where we're sort of leveling out to a point. It looks like at about x or at about y equals 1. And I'll go ahead and add that as a horizontal asymptote now. And again, I like to make those asymptotes dashed black lines. That's kind of a standard that we commonly see. And if you wanted to visualize that horizontal asymptote, we could use the table of points to check the long run behavior. That would be essentially looking at what is the value of y doing as x approaches a really large amount as we travel down the x-axis. So I'll go in the positive direction first. Just putting in 100, 1,000, 10,000 and continuing to add zeros, we see that y value approaching a value of 1. And if I change that to a negative, we will also approach 1, but just from the bottom side. So looking at the graph, that would be tracing it out to the right, seeing it approach 1 from above, and to the left, seeing it approach it from below. And other than that, you might consider adding things like intercepts. The intercepts are found in a couple of different ways. We can always find them visually. Here looks like we don't have oh, here we go. Here's a y-intercept and here's an x-intercept. We don't have an intercept on that positive x or y axis, just both on the negative sides here. Now you can extract points from the graph using this button and put it in the list, but I also encourage you to think about where these intercepts come from. We've already established that f and g are essentially the same other than the whole, which we've identified, so we can really focus in on g of x. The y-intercept is when we set an x value to 0, so we see that there, which means we could actually add our point to represent our y-intercept. I'll add a note for that. Y-intercept is at the point 0, g of 0. And there we see that added in as a point that is tied to g of x. I'm just changing that to blue. And I'll put in my x-intercept as well as a note. There's my label. And my x-intercept is when the y value is 0. We see that there. So we essentially want to set g of x equal to 0. And that's only going to happen when the numerator is 0. So x plus 4 in the numerator is 0 at x equals -4, which we can confirm here. And I can type that in as -4, g of -4. Now, it's not necessary to use this function notation every single time, but it's really nice to use that existing coding that we've used, defining the function up here, and sort of take that possible error out of the process, really just identifying an x value that we want to evaluate the function at and create a point there. Now we see both the x and y intercepts as really prominent points on the graph. Those points were always there. If I remove them, they're still there. We just don't make them bigger dots unless we really want to bring out that detail like so. Now I've got a rational function with a lot of key features that are labeled. I have a couple different versions of it, one with that whole discontinuity, one where we simplified that out. This is a really great way to study all those different features of graphs that we can then sort of pair up with all these concepts such as domain, the whole, vertical asymptote, horizontal asymptote. There we see some rationale for why it's y equals 1. And this ChatGPT gives us a final summary of everything to really check all the work in that process. So I like the kind of the process of taking the function, factoring it out, and just examining it without the work and seeing if we can make all those features come to light. Then we can go and check it against the work and see if we've done all of those things correctly. If we have, we'll really see a nice picture where everything's aligned and the graph is kind of steering away from these asymptotes, and we can trace through and find those holes that align with those points that we put in ourselves.